Hello YouTube! Today we are going to talk about forces on an inclined pane. And an inclined pane has two major attributes, which is it's a pane, so there are no bumps in it, and it's inclined, so it actually has an angle compared to the horizontal. In the end, that looks somehow about like this. And I've put an object on this inclined pane, on this green inclined pane here with the angle phi. And this object is going to experience a force, which is the force of gravity. And the force of gravity goes about downwards. But there's one problem right here. We have no idea how objects interact with forces that go downwards. We actually don't know anything at all right now. So let's scroll a little bit to the right and I'm going to tell you what happens if a force just goes plane downwards. If a force goes plane downwards on a normal pane that's not inclined, so if the force is actually orthogonal to my pane, so if it's normal to my pane, or you could say that it has a right angle, then we have one very interesting thing. The object doesn't just think through the ground. It doesn't. Instead, the ground applies a backward force against the object. So we actually have a backward force so that each force cancels out. The backwards force and the forwards gravity force cancel out, and we have the total of forces is equal to 0. So our velocity stays the same. Usually the velocity is just 0, but if the object would, for example, move to the right, we would have the same velocity. Another possibility is when the force is actually parallel to our ground, parallel to our pane. Then we have force equals to m times a, which is just Newton's law of motion, the actual action principle. So let's get back to our example and see what two directions we can actually use. We can use the direction parallel and orthogonal, or is right angle. Orthogonal and parallel. Those are these two directions. So we actually have to divide our force into those two directions because we only know those two directions. So how do we do that? Well, we do that by applying our knowledge that we learned about dividing and adding forces. So we divide these two forces. How do we do that? Well, we draw a parallelogram. So we have this line right here, which looks somehow about this, and we should get this one right here. And now we can get the two components of our force, the one which is just orthogonal and the other one which is just parallel. So orthogonal and parallel force we have right here. Now those two forces have a special name. The one is called the normal force because it's normal to our pane, and the other one is the downhill force. That's pretty cool and all, but what are they? How big are they? To answer that, we're going to have to look at them a little bit more. Here you can see a very rudimentary drawing of the pane in which I put the angles. We know that the parallel force line and the orthogonal force line both have to be at a 90-degree angle because one is parallel, the other one is orthogonal. And what we also know is that our x direction and our y direction are orthogonal. So we have two right angles right here, and they are going to help us to determine this angle right here, which I already labeled. Now let's not spoil the fun and let's think this through. Here we have a rectangle with a right angle, and in each and every rectangle all angles have to add up to 180 degrees. So this angle plus this angle plus this angle have to be 180 degrees, or these two have to be 90 degrees because this is already 90 degrees, so we only have to get up to 90 degrees. So this one has to be whatever is left, 90 degrees minus my angle phi. Now the rest is pretty simple because we know that these two also have to add up to 90 degrees, so this one has to be phi, which is what is left of 90 minus phi, to get to 90 degrees, which means that we can actually derive our components, our normal force and our downhill slope force, by using basic geometry. We know that this is a right angle because this is just a parallelogram, so these have to be right angles, and we also know that this downhill force slope force, which is up here, is also down here because that's a parallelogram. So in the end, we see that here, down here is the downhill force slope, and this down here is the normal. So we get the norm of the vector of the downhill force, or simply the magnitude of our downhill force, by simply making basic geometry. We know that this is the opposite leg and this is the hypotenuse. So we take the opposite leg over the hypotenuse, which is thus the sine. So the sine of phi is nothing else but the opposite leg, f downhill, divided through the hypotenuse, which is thus our gravitational force. And we can do the same for our normal force, in which case we have the adjacent leg, so it's the cosine, and the adjacent leg divided through the gravitational force, which is just our normal force divided through our gravitational force. We can take those two formulas and put them in another form, which is this form right here, which just depends on our gravitational force. So we need to know a mass and we need to know the gravitational constant on the Earth's surface. If we have those, we can actually calculate our normal force and our downhill slope force. Now there's a pretty interesting fact that we can also calculate what our acceleration is going to be. Our normal force just does nothing, while our downhill force is going to accelerate us. Our normal force is getting countered by the counteractive force against the normal force, but our downhill force is just going to accelerate us. So it is equal to m times a, m times our acceleration. So our acceleration in magnitude is actually just our downhill force divided through m. And if we substitute the formula for our gravitational force, which is m times g, into our formula for our downhill slope force, sinus of phi times our gravitational force, we get this huge formula right here. And we can actually see that the masses cancel out. So we're left with sine of phi times g. So our actual acceleration is independent of our mass. We are always going to be accelerated with sine of phi times g. Well, what does it say us? Well, it says us that if our incline is at a 0-degree angle, we actually have the normal force being equal to the gravitational force, because the cosine of 0 is just 1 and the sine of 0 is 0. So our downhill slope force is going to be 0, and that means our acceleration is also going to be 0. While if our incline is exactly at 90 degrees, our normal force is just going to be 0, and our downhill slope force is just going to be our gravitational force, which means our acceleration is just equal to g, which is quite interesting. So in the upper case, we have actually reproduced what we have looked at up here. Our special case of, let me remove this one, of our gravitational force just putting downwards, and we saw that nothing happens. The sum of all forces is 0, we don't have an acceleration, and that's what we see here again. In the other case, we have actually reproduced the case of falling. Here we fall with a equals to g. So if we had an initial velocity, we could actually once again do the formula x of t is equal to 1/2 at squared, and you know how it goes, plus and so on and so on. We could actually do that once again. Now for everything in between, we actually have to substitute for a formula 1/2 at squared and so on. We actually have to just substitute sinus of phi times g. So it would look about like this, while we have to remember that our force is actually pointing downwards, so I've added this minus right here. So then we have 1/2 sinus of phi gt squared plus v0 times t plus x0. Now instead of using this force right here, this completely normal force right here, we can actually do something else, which is adding friction. With friction, we still have this opposite force, but we also get another force, the force of friction. And seeing this, you might think to yourself, isn't the third law of motion violated right here? Because we don't have an opposite force to the friction force, do we? This is just a velocity vector, this is not a force. So what's the problem right here? Well, the problem is no problem actually. We have another force. I just haven't painted it yet. because the other force is actually in our body itself, in the ground itself. The pane itself experiences the opposite force to our friction force. But we don't see that because the pane actually has an acceleration of near to 0, or the ideal plane would have an actual acceleration of 0. So we don't see that, but it's actually there. The interesting thing once again is that it doesn't interact on the same object. This friction force is interacting on our object, while the friction force on the pane is interacting with the pane. Both the normal and the opposite to the normal force are both interacting on our object. That's why they cancel out. Now this is the formula for our empirical friction force. Empirical just meaning that it hasn't actually been found as a physical principle, but actually just by testing out, by making experiments. So this is actually an experimental force right here, an empirical force. We have found that our frictional force actually behaves like our normal force, just that we have some coefficient in front of it. And you can look that coefficient up in any book or any table, and you just look at coefficient of friction, sometimes also COF, and there should be some COF formula, not formula, but COF table, that you can actually look up what your friction is, what your coefficient of friction is. Sometimes it's also a Greek letter mi instead of this lowercase f, but I'm going to use this lowercase f for now. So what else is there? Well, otherwise there are two things that are additionally here, because two things that we wouldn't really need to describe this force, which is this minus and which is this EV vector, whatever that is. Well, I can tell you that's actually the unit vector of our velocity. What does that mean? Well, this is nothing else but the direction of our velocity. So I'm multiplying the magnitude of our force with the direction of our velocity. So I'm saying, oh, this has to go in the direction of the velocity, so in this direction. Well, I'm not saying it has to go in that direction, but in the opposite direction. So this is why there's a minus here. So the minus ensures that our force is always going to point in the opposite direction of our velocity. We can just remember that. If we remember that, we only have to remember that the force of our friction is actually equal to this coefficient times our normal force, or sometimes this coefficient times our normal force. Now there's one problem with remembering this, because the one thing you don't remember when you remember this is that when the velocity is actually the zero vector, the null vector, we actually have a problem. So if we don't have a velocity, our friction does not actually exist, and that's something we like to forget very, very, very easily. But we should remember it, because it means that our friction cannot actually accelerate us. It can't. You will think that if this velocity is getting smaller and smaller and smaller, and the friction force is just staying the same at all times, independent of our actual velocity, you will think that if our velocity gets zero, the friction force would further apply and accelerate us in the opposite direction. But that's not true. Once our velocity reaches zero, our friction force is satisfied and stops completely. But until then, it's actually always pulling with the same acceleration, or the same force, I should say. So if we have a velocity of 10 trillion billion quadrillion, we actually have the same force of friction as if we had a velocity of 0.00001. The velocity does not matter at all. As I said, that's an empirical force, and if we would really look into it in nature, and we would do thousands of tests, we would probably find that's not exactly how it is. But it's a good estimate. We are also going to find other forces of friction, but this is the first one we are going to see, which is its magnitude, I should say, is actually just this coefficient times our normal force, and the direction is always opposite to our velocity. If we don't have the velocity, we don't have force of friction. So in the end, we can actually find two more forces if we are very exact. So here we had two forces, but that wasn't really exact, because we actually had one more force, which was the opposite force to our normal force, which is applied by the inclined pane onto the object, as we saw, so that it doesn't just sink into the inclined pane. And we additionally also can have a force of friction if we use friction. If we don't use friction, we actually just have the downhill force, the normal force, and the opposite force to the normal force, which we really don't care about. And we have the acceleration of sinus of phi times g. Now if we add the friction, we have these two formulas being just the same as they were, but we actually get another one, which is our friction force, which is just going to be our normal force multiplied with some coefficient and in the opposite direction of our velocity. So it's probably going to be the opposite direction of our downhill force, but it can also be the other way around. If we have this object actually gliding upwards, we actually have a friction pulling it further down, stopping it faster. Let's just talk about the case that we have velocity going downwards though. It makes things a little bit easier. In that case, we can say that the force of our friction is actually going to be cosine of Fg, which is just our normal force, times the coefficient, or mi, you could also substitute mi there, but then we add this minus here. And we add this minus because now we're looking in the direction of the downhill force. So we're looking in this direction right here. Remember that, because otherwise we would have to add the direction right there. So our total force in the direction of our downhill force is just going to be our downhill force added to this friction force. And this friction force is negative because we're looking downhill. If we were looking, if the velocity was going uphill, we would just have a plus right here. So I can actually add that right here with another color. I'm going to choose this light gray color here. So if we actually have the object going up the slope, we actually have plus right here. So it's being decelerated even faster. If we have this object going downwards, we have this minus here, so it's going to get accelerated downwards even slower. Now right here I have only pulled out the factor Fg and bracketed it out here, so Fg times this bracket. And if we do that, we can actually calculate our total acceleration once again, because our total acceleration is just going to be F equals m times a. I can write that down here, and our Fg is just m times g. Our gravitational force is just our mass times our gravitational acceleration. So our total acceleration is going to be a is equal to our gravitational acceleration times some factor. And that factor is either sinus of phi minus cosine of phi times Fn if the object is going downwards, and sinus of phi plus cosine of phi times Fn if the object is going upwards. In both cases, this is the downwards pointing acceleration, because I assumed that we are looking downwards at all cases. So remember that, please. So if we go upwards, if our object goes upwards, we have this force that's quite big, that's the added force. And if we have an object that's going downwards, we have the smaller force, because our downhill slope force is subtracted by the friction force. Now what's interesting is if we take Fn is equal to 0. That's very, very interesting, because we're actually going to see one interesting fact if we do that. If we do that, this is 0, so this whole term here is 0, and we don't care about the plus or minus anymore, and we get g times sinus of phi. Now, if we remember correctly, g times sinus of phi was actually what we had up here, because we actually used, without even knowing, the principle of specification and generalization. If we generalize some specific cases, like these two cases here, we took these two special cases for an uninclined pane, and we applied these two special cases to our generalized case with a tilted plane. A tilted plane would be quite strange. So we took these two special cases and generalize them for our special pane. And what we have to have is that if we take our specialized case and we specify something, we actually have to get our specified cases again. So if we take our generalized case with the angle phi and we specify that the angle is equal to 0, for example, we should get these results. And did we get them? Of course we did. Of course we get it. Right here we did get them. We knew that our normal force is just our gravitational force and our downhill force is equal to 0, and that means our acceleration is equal to 0, which was just this case. Here, right here, we have our acceleration is equal to 0. So whatever we generalize has to also apply in the specified case. Now let's go down here, and down here we generalize that there should also be a possibility for friction. Now if we remove that possibility again, we specify it again, and we have to remember that this generalized case has to also apply for our special case, which is by putting Fn equals to 0, that's our special case, we can actually test if this formula is correct, because it has to apply for our special case. So if we take the special case Fn is equal to 0, this cancels out and we get our special case once again, g times sinus of phi. So if we go from special cases and generalize it, the generalized case has to always apply to our special case. And that's how you test your formulas. You test them by specializing them once again and looking if it still works. And that's a cool thing about physics. Any generalized formula has to also apply for the specified case. There's one last thing I want to talk about, which is how do we get that our acceleration is equal to 0? And that's pretty simple actually. We look at this coefficient down here, and we're just going to assume this object has, well, no velocity. But we're not going to assume it has really no velocity. We're going to assume it has a really small velocity going downwards. And we're just going to assume, going to look at when is the acceleration actually 0. This is pretty simple. We are going to just take this formula for our acceleration and substitute what happens if it's 0. We divide through the g, so the g goes away, and we have this right left, and I put the phi critical here, so that's our critical angle, because that's what it's going to be called. And if we do some math, we actually get that our coefficient mi, or Fn, is actually equal to the tangent of this critical angle. What does it mean? Well, it means that the slope with the angle that's lower than our critical angle, so the angle is lower than our critical angle, then an object that's on here is not going to move, or at least it's not going to start moving. If it already moves, we have to take the plus formula and then things get difficult. But if it doesn't move, it's not going to start. But if you have a plane tilted like this, where our angle is actually higher than our critical angle, we're actually going to see that any object on this pane right here is going to start to move downwards. And that's a very interesting thing, how you can measure our coefficient right here. You just take a pane and you see when does my object start moving if I tilt the pane more and more. And when it just starts moving, you have just reached the critical angle, or are just above it. So by that you get the critical angle, and by taking the critical angle over this formula you actually get this coefficient. So that's how people tested the coefficient and how those tables of coefficient actually started and being made. So what did we learn today? Well, we didn't just learn about forces on the inclined plane, we learned much more. We learned about the principle of generalizing and specifying, that if we generalize whatever thing we want, then it has to always also apply for our specified case, and that's always so, and that's going to be in every video. We're going to generalize something, or in about every video we're going to generalize something, and it has to apply for a specific case. Now on the inclined pane, we actually learned that we have to divide our force into two parts, which is the part parallel and the part orthogonal, because we only know how forces interact when they're parallel or orthogonal to some pane, which is these cases right here, parallel and orthogonal. And then we looked at these components, the normal and the downhill force, and the normal force does at first nothing if we don't have a friction, and our downhill force is just going to be equal to m times a. By that we can derive a formula for acceleration, which is just going to be sine of phi times g. If our incline is at 90 degrees, we are going to get the special case that our a is equal to g, so we have the case of falling. Remember, the direction of this is actually minus. And if we have an incline at 0 degrees, which was this case up here, we actually have no acceleration as we expected from up here. So again, the generalized case applies for the special case. So if we add friction, we generalize it once again and we add the friction, we actually get this empirical formula for the friction, which is just this friction coefficient times the normal force, and that in the negative direction of the velocity. So in the opposite direction of the velocity, we have this friction coefficient times the normal force. By that we derived the formula for our acceleration, which is when the object is going up the slope, we are going to have an acceleration down the slope of g times sine of phi plus cosine of phi times fn, or our friction coefficient. And if the object is actually going down the slope, we're actually going to see that our acceleration is the gravitational acceleration times sine of phi minus cosine of phi times fn. And finally, we talked about critical angles and how we can tilt a plane to the critical angle, and after that critical angle, every object is going to roll down or fall down that pane, and before that, the objects are just going to be stationary. There's not going to be any accelerations. As you might find out, if we substitute some values right here, we can actually get a negative acceleration, but that is only because the angle is going to be lower than the critical angle. And then we have to remember, oh, the acceleration isn't actually negative, it's just the critical angle. How do we get the critical angle? Well, we just take this formula right here. Our friction coefficient is the tangent of our critical angle. So this formula right here only applies if our critical angle is is bigger than the arctangent of our friction coefficient, which is either that or the Fn. Both are possible. I hope you enjoyed the video. I hope we can see each other next time, and goodbye. Tschüss.